Good afternoon, everyone. Welcome to the afternoon session. Let's start the session by calling Yinyi Li that will talk to us about quantum information science in particle physics.
Thank you. Okay, so it's my great pleasure to be here, and thanks a lot for the invitation. My assigned topic is quantum information science in particle physics. You see, it's a very broad two topics, but now they are converging to one. So given the limited time, I will focus on these three aspects from quantum information science. And the first one is quantum sensing. As you already see from the morning talk, we have utilized this technology in our detectors from the morning talk. And I would like to highlight a little bit of the recent results. That is a tabletop experiments where you have actually using the CAT state, which is a superposition of the coherent state to detect the dark matters. So once you put the sensors on Earth, and then we have all of this gravitational waves, dark matters, photons, and neutrinos coming by. Suppose you have a dark matter that is the dark photons. Then with this equipment, we can probe this dark matter, the mixing angle. Sorry, okay, yes, the mixing angle by like 2 orders of magnitude. Right. This is a very excitement that could bring us by the quantum sensing. And then the second topic I would like to mention is quantum information theory. That's we have a lot of long-term efforts in probing like violation of Bell inequality and also the quantum properties in the condensed matter, also atomic theories. And at colliders, this is a very unique avenue for us to probe the quantum rhythm at very high energies. You already see this very nice result from Atlas that's measuring the entanglement from the TD bar final states. I would like to highlight a little bit that this route, this is exactly from the quantum information science to our new observations of these quasi-particles that has been recently observed from CMS and Atlas, right? So we would like to emphasize with quantum information at colliders, we would push the new frontiers of probing, for example, the physics beyond the standard model. And then for my next talk, for the rest of my talk, I will be focusing on this quantum computing and the algorithms. So I would like to see this is really a new computational paradigm. As a theorist, given these new computers, I'm very excited as we have been troubled by a lot of computational challenges in particle physics. That is to say, for the path integrals in the quantum field series. So to do path integrals, we have method that has been developed since like 1970s. It has been already 15 years. This is in the non-perturbative region, we would have this lattice QCD, right? And it's doing the calculation with a classical method, which is go to the Euclidean spacetime, and we can do the Monte Carlo method. After 50 years of development, it has achieved a great success in studying the static properties of QCD, which you will see more from tomorrow's talk, Andrea's talk tomorrow. However, as we care about the colliders specifically, we know there are a lot of real-time dynamics at colliders. For example, the parton distribution function. And quite recently, we have measuring these energy-energy correlators inside the jet. This is from the parton evolution to the jet. We can measure this quantity to probe exactly what is the confinement and the perturbation and these free hadrons. It tells us a lot about the confinement in QCD. But given this real-time dynamics, we don't really have a non-perturbative path integral to do the calculation and predict these energy correlators. Our current tool is based on these probability splitting functions that is summing over all of the histories classically and also with the fragmentation functions fitted from data. So you can see our current prediction based on the models and also classical summations give us a very large uncertainties. This is a blue shaded region here. But our measurement has achieved a very precise limit here, precise measurements here. So in order to improve this precision and also really perform this path integral from first principles, we cannot rely on this classical method, but because when you deal with the real-time dynamics, it will give you the sign problems. This is one example I think most of the audience care about. Actually, we have listed a bunch of problems in high-energy physics, for example, also including the finite density out of equilibrium dynamics in the early universe, etc. in this paper, and to highlight what are the problems or processes that we care about. However, the classical method cannot be effectively solved, right? Which is to say, if you use the classical method, it will cause exponentially large computational resources as we increase the system size. And this is a non-perturbative region, right? We also have the path integral in the perturbative region. As you can see, this is the Feynman integral method. It also started in 1970s. It has been 50 years. And our current status, for example, if we care about this ZH production cross-section at the electron-positron colliders in the future, this process, our current prediction, which is at the next linear order, including electroweak and QCD corrections, the prediction could reach like 1% level. This is a very precise number. But for our future, when we have this CPC or FCCE that the large community is pursuing for future colliders, our target for this precision measurement of this quantity could reach like 0.5%. Right? So that is saying if you want to rely on the precision measurement of this process to probe physics beyond the standard model, we have to improve our theoretical calculations of this number. However, as you can see, this is a very naive cartoon of the current status of the perturbative calculations. If we want to push a calculation to the 3-loop orders, then this is only a very limited applications here. That's very, very non-trivial to include the electroweak and the QCD calculations. Another issue is we don't actually have a convergent perturbation series when we do the Feynman integral. It is asymptotic, but it's not convergent. So we cannot really tell once we include the 3-loop order calculation whether we can reach this precision or not. So given these computational challenges that we have considered, like for the whole community for like 50 years or so, we would be really happy to see once you have a new computing paradigm what we can do, right? So this is the current understanding of this new computing paradigm. So it is built with this quantum system. It's built of this 2-level quantum qubits, right? And so it has to be a quantum qubits because if we want to encode the quantum features in our quantum field series, then we have to use a qubit to encode a very exponentially large qubit space. This is the system conjectured back in 1980s, and then later, like 4 years later, we have learned that if you have this computing system, we actually could build up this universal quantum gates. It's a very small set of gates. However, with this small set of gates, we can actually achieve the time evolution operator to any precisions, right? So this is a very big achievement. So it's definitely saying you can build up this digital quantum computer that out of these building blocks here. And then later, for our interest, in 1996, Seth Lloyd proved if you have a local Hamiltonian, and then with these computing systems, we can achieve polynomial complexity. That is saying, if you want to simulate the corresponding Hamiltonian with these evolution operators, the number of operations required is also a polynomial function of the system size. Right? I would say these 3 blocks give us the theoretical foundation that once you have this computer, we can really simulate a QFT dynamics with polynomial complexity. It's very promising. However, we know as a quantum system, it's very sensitive to the noise, right? We need a very large quantum computer to simulate our field dynamics. So it's a very that we need the theoretical foundations of building up these large-scale quantum computers. And that goes to this 1995, when Peter Shaw developed this quantum error correction code, and also with the quantum threshold theorem. So with this theoretical foundation, it really tells us, in principle, you don't have difficulties of building up a fault-tolerant, large-scale quantum computers. Right, and also we know there are a lot of news going on today. Different companies have built up their different quantum computers, and the most powerful one could reach around 1,000 qubits if you operate with the experimental locally. So this is already beyond the classical computational capabilities. Okay, with this machine, then we would really see if I have this computer, I would like to do the path integral, right? We can do it non-perturbatively. It naturally translated the path integral, naturally translated to our path integral to these Hamiltonian formulations, right? We can prepare our quantum field theory to this, with these two steps, translate our quantum field theory degrees of freedom into a finite number of qubits, and then we can write down its corresponding Hamiltonians. And then with the Hamiltonian, we can prepare the initial state and do the time evolution and then measure the variables that we are interested in, right? It's a very natural framework, and as it is doing this, the lattice field theory in real time, there's no sign problems. So this is a very nice framework that we would like to ask, in practical, can we really achieve quantum advantage? That is saying with polynomial complexities when we simulate the QFT dynamics, right? So that we can first consider the scalar field theory as the simplest quantum field theories. So basically, it's quite straightforward to write down what is the Hamiltonian for the scalar field series, right? As we consider quantum field theory, we need to write down the field as an operator. This is the second quantization. Then you will see this mass term, and there's this lambda phi for interaction term, and also there's a canonical momentum term for the scalar field series. And importantly, we have this commutation relations related to the phi operator and the pi operators. So then in 2011, Jordan Lee and Preskill, they actually proposed, once you have this very nice basis, so because phi is the operator, I can directly work out its diagonal basis, right? And then its eigenvalue would be taken some values of phi. So in order to translate the continuous variable into finite one, we can discretize the phi field values into a finite set of numbers, right? So once you have this basis, we actually can show the quantum algorithm for the time evolutions. For example, for the mass term, could be implemented with a polynomial function of system size, as well as the interaction terms here. And the non-trivial piece is the kinetic term, right? It's the pi squared term. The most surprising part is given the commutation relation between phi operator and the pi operators, we can write the time evolution operator for this pi square as a quantum Fourier transformation circuit, and then times this diagonal matrix, and then you can do a Fourier transformation back. What is important is this quantum Fourier transformation, the algorithm is exactly the same as a quantum Fourier transformation algorithm in factorization, which was proven to have quantum advantage by Peter Shaw in 1994. So this is a very excitement in 2011, and then later people tried to extend the study to the scalar field series, to the gauge field series, which is our ultimate goal to achieve simulations of the particle physics, right? We can similarly write down the gauge field and its Hamiltonians. Here you will already notice the difference, right? Because of the gauge symmetry, in order to write down the gauge invariant Hamiltonian, we need to work with the link operators here. This is, with a link operator, we can form this gauge invariant Wilson loop. Also, we can write down its canonical conjugate momentum operator corresponding to this U hat operator. And then you also have two corresponding bases. One is diagonal in this U basis, U operator. The other one is the diagonalized in this L operators here. And then also we can write down the commutation relation between these two operators for the gauge field, right? You already noticed the difference, right? It's not as simple as the scalar field theory where you have a delta function on the right-hand side. So this is a non-trivial, and it's our ultimate goal to show whether we can achieve polynomial time complexity as in the gauge field series. So that is the current status. So given this, this stage, we need to translate our gauge field degrees of freedom into a finite set of qubits. There are different proposals, either based on this Kolge-Saskin Hamiltonian in different bases, or you can take approximation which only give you exact QCD calculation in the critical points. Right. This is a very vibrant research direction, and let me show you one example that is presented in the parallel talk. So this is the method for digitizing the gauge field into a finite set of qubits using the discrete subgroup. So we already mentioned the field value. This is U. This is the eigenvalues. It's for SU2 gauge series. It takes any value on the three spheres. And if we want to translate the Hilbert space into a finite set, we will translate this eigenvalue, the infinite number of eigenvalues into a finite set. So the eigenvalue only take this set of values. Then we can map the Hilbert space into like 8 qubits in this method. And then also, given the group property, we have this time evolution operator for the connected term, also related to this U basis by a group Fourier transformation. But it's non-trivial to say whether this group Fourier transformation could have the same time polynomial time complexity, the scalar field or not. Right? It's an unanswered question yet. However, this method could be extended to general finite groups, such as the largest one of SU3 gauge series. And also, based on this, we have worked out this gauge fixing circuit. This is a non-trivial ingredient to achieve this physical results. Right? We need to project our redundant Hilbert space into this gauge invariant Hilbert space. All of this work has been worked out. And the question remains is how to systematically approach a continuous SU3 or SUN serial limit, right? Because we only have a finite set of gauge groups. But I would like to mention that we still lack of efficient algorithm for simulating gauge field series, but this is a very active direction, so stay tuned to see the ultimate results. And then there's also this initial state preparations. For example, if you are interested in PP collisions, because our Hilbert space is written in terms of the gauge and the gluon, the gauge boson and the quark degrees of freedom in the free theory, we need to prepare this bound state out of these free degrees of freedoms. Right? This is non-trivial. Right? It's an inverse problem of PDF. However, given the development of quantum algorithms, there is this quantum variational circuit to find the ground state, because we can identify the proton state as a ground state with a certain baryon number equals to 1, right? So this is also a very valid method to prepare the ground state. And then quite recently, we have developed this machine learning method to extend the circuit to larger systems. Right? Instead of training every circuit for different system size, we can extend this circuit by extrapolation to large systems. So it works pretty well. As you can see here, this is a comparison between the variational circuit and the exact ground state energies. And the next step would be extend this method to the non-abelian gauge series that we are ultimately interested in. So I would like to spend like 1 minute to talk about one benchmarks. So previously, it's focusing on 3+1D particle physics developments. And given the current status of the quantum computer hardware, we can study some 1+1D toy models. And especially as we are interested in collider observables, for example, EEC, we can utilize this 1+1D Schwinger models. And then we can cook up a process. So at t equal to 0, we can inject some energies in the center. This is very similar to the TPP collision, right? You inject energies in the center. And then you see how the energy flows as the time evolves under the given Hamiltonian, right? We can put 2 detectors in different positions and then measure the correlations, the energy correlations that has been reaching these detectors. Right, you will see this is a simulation result we're using tensor networks, but it shows qualitatively correct physics. Basically, because the particle being emitted once you have this source here is relativistic, then we only observe the correlation when the time equals to the position. Right? This is a relativistic movement of the particles. And I would like to tell you, like, we have currently working on some predictions that could match the correct continual limit, so stay tuned for this very exciting results related to collider observables. Also, the previous one is a non-perturbative path integral. I would like to highlight some studies presented in the parallel talk, like that's trying to accelerate the perturbative calculations. For example, you have this phase-space integration related to the Feynman integrals, and instead of using the gradient cells, we can map the gradient cell with a number of qubits, such that we can reach like a very stable result in the phase-space integration. Here is showing with quantum method, you can basically deliver smaller uncertainties in comparison to classical ones. There's another possibility I would like to encourage people to try is, for example, for the two-loop level calculations, if you consider the intermediate step, you will have a very large number of linear algebras. Here is an example. It's a two-loop level calculation. The number of linear equations is 10 to the 7. This is thanks to my colleague. And for quantum algorithm, we know there's a HHL algorithm that could achieve this log complexity. It's a log function of the number of linear equations. So then the question would be, could it prove a new computational paradigm, right? And then there's also this computational challenging experiments that I learned a lot from my experimental friends. So here is a very nice roadmap article formed by CERN, IBM, and DC. They list all of the challenges, computational challenges in experiments, like track reconstruction, and also these Python showers experimental simulations. So this is even though all of the different computation is a polynomial function of the system size, but we can pursue whether quantum simulation or algorithm could help us to accelerate the data analysis, right? So here is two examples. One is based on the jet reconstruction. The other one is a track reconstruction. Here we can already achieve like a comparable precision as a classical method using quantum algorithms. And this one here, once you have a quantum layer, it's a quantum circuit layer, basically the accuracy could be improved a little bit, and also the parameters inside of the quantum circuit could be reduced. Okay, so given the very limited time, I will just make the long story short into one sentence. It's quantum information science has opened a very different frontiers for particle physics. As you can see, there are still a lot more remains to be explored. So I will just encourage to wait for the excitement. Thanks a lot for the attention.
Thank you very much for a nice talk. So I believe we have time for 2 questions. Oh, okay, I see one hand over there. I can't see because of the light, so yes, please.
Thanks for the nice talk. I just wonder, in the normal lattice QCD calculation, we have to worry about taking the continuum limit, and this has to be done very carefully. Now, I'm just wondering, when you also end up discretizing your thermals, and I wonder, do you encounter a similar issue in recovering the actual continuum dynamics that you're looking for?
Yeah, exactly. So the calculation in real time is also based on the lattice field theory. We need to take the continuous space-time limit. And that is under the investigation because you see our current status is still developing the quantum algorithms at a finite lattice spacing. There are currently 2 papers studying the continual limit. One is based on the classical lattice calculation method using the skew setting, etc., non-perturbative skew setting. The other one is just to take the space, the lattice spacing to be a very small value, and you can use extrapolate to continue with polynomial functions. That we have to guarantee the lattice spacing is pretty small. And also for this observable, especially for energy-energy correlators, we can achieve the continual limit at the critical point. That is another way to achieve continual limit predictions. But I would like to say there are still a lot of things to be investigated to reach a continual limit, as you said, yes.
Okay, so time's up, so thank you very much.
Thanks. Thanks.
And now let's call Kate Shaw, and she'll talk to us about the initiatives of outreach and education in high energy physics.
Okay, hi everybody, good afternoon. So it's my pleasure to talk to you today about outreach and education HEP. Just want to draw your attention to this cute photo by the Atlas detector with some stakeholders visiting just a few weeks ago. So I want to start with the question of who does high energy physics belong to? And I think we all know the answer is that it belongs to everybody. We're really lucky to be able to work in this field, but it's really our responsibility, and we all know that we should be doing this, to communicate what we're doing and reaching out to public students and policymakers to communicate what we're doing and why. And we also have very ambitious goals that we want to achieve in high energy physics. And to achieve these, we need continual national and international support and funding. So we've had a lot of wonderful results over the last few days, but I think we all understand that scientific excellence, it doesn't automatically translate into public or political support. We actually have to continuously be communicating with the public and policymakers. We need to continually build understanding of what fundamental high energy physics really is. And why it takes decades, I think, is a really important message we have to continually communicate. We need to talk about what the impact to society is. We need to think about why national and international infrastructure matter. And finally, we need to communicate to policymakers that if we reduce scientific capacity or we lack investment into infrastructure, it takes a long time to rebuild these things. So I want to talk to you today about the scientific ecosystem and the role that outreach, education, and communication play. So in this ecosystem, oh, can I go back one? Yep. We start off with the research. The research is obviously what we've been doing in our experiments, our computers, and then we analyze this information and we create papers and we present at conferences. We create knowledge, great. The next step, of course, to get that open and to the public is we need to then open out science. We need to make our data sets available for theorists, for educators, for students to be able to access to. Okay, once this is open, we can then do education then to secondary school students and primary school students. We then need to do public engagement and communication to create dialogue and shared ownership. We need everyone to feel part of this experimental journey. And then once this dialogue, national dialogue, is established, this can then lead to policy engagement, which allows us to reach our goal, which is to allow our long-term science to flourish. Oops. And so if we start, so I've got just some tags at the top here showing where we are in the ecosystem. We start with some of our wonderful results that we've had so far, and we turn to open science. So the first step is from all the results we've been having and discussing this week, can we open our science and make data for everyone to have access to? Open science is really important, not just in physics, in all of scientific industries. It's a push from UNESCO, and they've really identified it as an important accelerator towards sustainable development goals. We really must do that. It helps bridge the gap between and within people within countries. And so CERN have really been an incredible driver of open science since the very beginning. On Atlas and CMS, we've been going about 12 years. CERN really started this at the beginning. And I love that they said this from their website. They said, at CERN, we believe that the practice of open science is key to delivering on our organizational message. So it's really at the heart of what CERN does. And these are the different levels. So if we start with raw data, level 4, for other types of science, like in astronomy, they do make this open. In the work that we do at CERN, this is often not feasible. But we do release reconstructed data, and this allows theorists and other types of students to access our data and to be able to do physics studies. Then we have level 2, which is a dedicated subset of data to make entiples that can be used for outreach and education. And then, of course, level 1, which we've always done, is publishing results in journals. So Atlas and CMS have been working on this for over 10 years. So Atlas, you can see, are kind of 3 things that we focus on. The first is on research, where we provide scientific community with high-quality Atlas data sets. The education aspect is very strong with Atlas. We really want to empower students and teachers with our data sets, real data, and we have lots of different ways you can access it. And then there's a focus on accessibility. You can see here one of our machine learning web applications so that people can start to understand how neural networks work without needing to understand coding and scikit-learn. And here we have CMS open data with their 3 levels. You can see it changes the invitation from read about our discovery to explore how our discovery was made. And here how we've implemented it. We've done machine learning training at the University of Bhutan. We went to Togo and did Atlas and CMS Conference of Physics and international masterclasses. So over 13,000 students a year take part in this. We have Atlas, Alice, CMS, Minerva, NERVA, or J. And we'd like to announce that now we have proto-June masterclasses, which introduce students to June, allow them to visualize cosmic rays interactions, which you can see here. Now, this is really fantastic. It's been developed by scientists at South Dakota Mines. Over 200 students have started working on analyzing this data, and it's been shown here at NATO in Brazil and in the US. So moving on to communication, we have big plans. We need to show the societal impact of what we do. This is through inspiration, education, high-level training. We need to communicate our news, our updates through press releases and through websites and social media. And we need to build trust with the public, inspire policymakers, and educate young people. So the goal of the communication is to make a sustained relationship between science and society. For the experiments, this means we need to communicate our physics results, our detectors, our hardware, our software and computing. And of course, we need to talk about the collaborators, us, scientists, technicians, and students. And high-energy physics actually already does remarkable in this area. We do global communications, news and blogs, social media, virtual physics, public events, and of course everything in multiple languages. So here are just some highlights. Atlas and CMS have some fantastic websites. They communicate things over physics briefings. This is a screenshot of CMS physics briefings where they communicate out their latest results in an explainable way. Atlas have been doing a fantastic job of leading on high luminosity so that all their communications are talking about the next era of high luminosity LHC. And we have NOVA and LHCb here that have really wonderful websites. For social media, I can show you some examples from neutrino sector. So June have been developing a really nice initiative called Global Voices of June. You can follow them on their social media platforms, where they really highlight, well, we're going to highlight all members of the collaboration and give them a nice bio and an inspirational quote about what they're excited about that's going to be coming up with June. Okay, we also have Bell 2 here, Microbeam and Nova, that use social media to communicate out about what's going on in the experiment, posters at conferences, and talks and group photos. Okay, so now we're going from public engagement to shared ownership and dialogue. One of the most important parts of outreach is really the communications that we do in person. This is really important because you're meeting people where they are. This creates one-to-one dialogue. You're connecting on a human level, and you can really have impact on the next generation. So you can see here some of the Atlas printables where you can really connect with primary school students over these colouring books. So really fantastic outreach going out in Pierre Auger and the Big Bang stage. So this kind of interaction is really the most important part of the outreach that we do. And then there's virtual visits. So Atlas, CMS, and Alice have been doing virtual visits for over a decade now. These are really important because they overcome the physical distance and bring excitement into the classroom, into science events, into public places. So these are really important, and it's been really nice to announce this week that Atlas published the first outreach published paper, and this is on virtual visits. You can find it here. So these virtual visits are live from down in the detector cabin or the visitor centre, and you get a nice introduction into the experiment, and then it's really about the Q&A. It's the dialogue between the people that you're talking to and the scientists. And this is, of course, done in multiple languages. You can see this wonderful dashboard Mohammed worked on, and this shows the number of interactions since 2019. So we've had 750 different visits in almost 70 countries, and that's since 2019, and we've been working, of course, since 2010. And you can see here this nice graph showing the different countries, and you can see Brazil is at the top, so there must be some great Portuguese Atlas speakers at CERN really working hard to bring Atlas physics around Brazil. There's also been some fantastic outreach being done in person here at ICHEP in Natal. This was led by Anna and other members of her team. It's been really impressive. I don't know if you've seen everything that's been going on. There was the exhibition, which is called The Physics That Connects Us, which is a really important title. Again, it invites the public to be part of what we do, not apart from. There have been scientific talks, masterclasses with Atlas CMS, June, and Pierre Auger, visits from the local schools, science and art, and yesterday there was the performance of the dancer particles. This has all been really fantastic. Okay, and finally we move in our diagram up to policymakers. So engaging in policymakers, we all know, is extremely important. It's important to get our messages correct and clear to people who obviously are very busy and have many things to worry about. So politicians are people we need to be having face-to-face interaction with. So you can see here two examples. One is here from the UK, where a set of people from high energy physics went to meet up at Westminster. So you can see Linda here, the spokesperson of NOVA. We have Brian Cox, a very famous science communicator in the UK, and Professor John Butterworth, who's the Atlas Outreach Coordinator at the moment. And they did an amazing job realizing this. We have to continuously communicate with policymakers. It's not something we can just do once and think we've done the job. We have to continuously talk to them and tell them our messages, tell them the impact, tell them the timescales. Here's another example over in the US. This is the high energy physics, a group of scientists that really go every year, annually, and they go to speak to all of the people in policy making directly. They've said it's really good, it's made a positive relationship. Obviously things go up and down, but the fact that they go every year, they make some fantastic outreach materials. And Professor Quinn has really said that doing this every year has really helped, at least within the people that they talk to say they really have a gold standard of planning. So I just want to end with talking a bit about the International Particle Physics Outreach Collaboration, IPOG. So there was a nice talk by Steve that you can see in the parallel. So this is an international collaboration for particle physics. It spans across the world with 34 countries, and high energy physics experiments are also part of the collaboration. If your country or experiment is not involved in this, I really encourage you to get involved. It's really a fantastic collaboration. The main thing that the group does is organize every year the international masterclasses across the world. It also organizes Worldwide Data Day, International Cosmic Day. But one of the things it's fantastic at is sharing educational resources, meeting up with people who are the experts of outreach, communication, interacting with policy all over the world, and sharing your resources and understanding. The next meeting for IPOG will be at CERN in November, so if you're interested to attend, please get in touch. So just to summarize, we've discussed the physics ecosystem today, looking at education outreach. Outreach is also really vital, I think, for everybody, especially early careers, to develop skills for communication. If any of you want to look into doing more, you can get in touch with the outreach coordinators or your institute's communication teams, or of course myself or the other people here. And also for the more senior people here, it's really important to help your country, region, experiment, university give value and support to those that are doing education outreach and communication. Thanks for listening.
We have time for questions. One at the back.
Hi, thank you very much for your talk. So I was wondering, all of this was more focused on experiments, but what could also the theory community do in order to improve our outreach?
Yeah, it's a great question. I think it's true that experiments do tend to lead the way because we're a collaboration, so you can share the kind of resources. But I think it's super important for theorists to communicate in just the same way, having platforms, so your own social media, of course, but interacting with press releases and website on your institute is really important. And then the same as everything else, having public events. Often when we're talking about particle physics in particular, people don't know if you're necessarily an experimentalist or a theorist, right? But I think that's a really good message for us to send.
Okay, another question here, Jota.
Thank you. Actually, a follow-up on this question. First of all, we have several theorists that participate in the master classes, and one of the upcoming master classes is exactly quantum computing. That is a perfect topic for theorists as well. Thank you.
Thanks.
Thank you. Any other question? Okay, here. Is it Leandro?
Hi, thank you for the talk. Nice talk. I would just talk about education. There are many different fantastic projects, but I heard from teachers, high school teachers, that they don't feel comfortable to deal with these subjects. And so the follow-up with the students is a bit difficult. Can you comment?
Yeah, that's a really good point. Thanks for making it. I think, yeah, doing stuff with, doing outreach with secondary school students and primary school students, excellent. But teacher training has a really clear role to play in that too. Now, I know CERN do a lot of work for teacher training with all of its member states. And I think you're right, to have any kind of longevity in the communication that we have, it's important to have teachers involved.
Okay, another question there.
Thank you very much for the very nice talk. I had a question on how to build local engagement and local presence in a context where a lot of the outreach efforts that are made are carried by early career researchers, which are by essence on temporary contracts.
Sorry, what was the question?
So how can you build engagement, long-term engagement with local communities when a lot of the people who are...
Yes. Yeah, that's a good question. I think if you're working from your institute needs to provide you the structure and support to be able to do it. You're right, a lot of outreach and engagement is done by early career people. And I think it can be more tricky because you need to have some sort of institutional support to be able to talk to schools, be able to know, local places where you can give public talks, and these sort of things. So I think, again, it's something that more senior people need to set up and support the younger generation to be able to do. Thank you.
Any more questions? Okay, we'll see here.
Yes, well, thank you for the talk. I just wanted to ask you, what are according to your experience, what are the things that are interesting for people who are not in the field when you try to communicate here?
What are the things interesting?
Yeah, because for example, I try to promote, particle physics in the experimental part in my country, this is Chile, and I usually try to say that, this involves industry, etc., etc. But some people tell me about the science. That's what's interesting, not about the business.
Yes. Can I have some water? Yeah, I think you need to really think about your audience. it's completely different messages for different audiences. You're absolutely right. I think when you go to like a festival, for example, you'll notice some people want to know about the engineering, detectors, other people want to know about fast and light neutrinos, and other people will just want to know what it's like being, you know, a theoretical physicist, what do you actually do every day. So the different messages are really broad, and I think it's just about knowing your audience to see what they're interested in.
Thank you. Any further questions? I don't see any hands on.
He just
Oh.
won't give me the microphone.
The light. Oh, I'm sorry. I couldn't. Okay, please.
Thanks very much for the very interesting talk. I just have been noticing these outreach efforts for some time now. And it turned out that the worst problem that we had when we lost our superconducting super collider project was because whatever outreach we were doing, we didn't reach to the other areas of physics. And it turns out that the solid state community, with some extremely influential people in it, attacked this idea vehemently. And we didn't have none of our outreach really went to other subfields of physics. And I could see that in your talk, I don't see any component associated with that same issue. And I want to say, it is one of the main reasons we did not have the superconducting supercollider. Not the only one, but it was a major contributor.
Thanks for the question. Yeah, I can't comment on why it was built or not, but I think you raise a really important issue, actually, and we have been discussing it a lot, that one of the communication avenues we kind of take for granted, but we don't put enough effort in, is to actually our colleagues within the field. We're pretty good at discussing with each other, and then we're quite good actually at communicating to the public, you can say, but you're absolutely right. With our experiments or our projects, communicating to other people within the field of physics is really important. Again, as we would probably put that in line with stakeholders or policymakers. We do need to communicate with them. They're going to be on panels that decide if we get grants or not. So I think it's something that people have been discussing more and more, and we need to look at how we can achieve that better. Thank you.
Okay, go ahead.
Hi. Thanks a lot. It's more as a comment. I think that from I can hear the audience, I think a lot of people are afraid of doing outreach because the colleagues, right, they don't know exactly how to bring what they do for the public general purpose. Then I think maybe you can highlight the channels that can help people to find resources and communicate with those they are already doing.
Yeah, thanks. I mean, yes, we're very happy. You know, the community, there's a big community that working education outreach. There's a whole track here at ICHEP and tracks at other conferences where people get together to present their work and also support each other. And as I said, each experiment will have an outreach coordinator or manager, and they can help people. And we're also happy to. So really, if you're interested in doing, you know, some education outreach or talking at events or organizing a festival, just get in touch with us. We're very happy to, you know, to help and support anyone that needs it. Thank you for the question.
Okay, we have time for one more question in case there is one. I don't see any, so let's thank Kate again.
Hi. So now let's welcome on the stage Flavia Almeida Diaz, who will show us some communications about diversity and equitable opportunities in our field. Thank you, Flavia.
Thank you.
Muito boa tarde para os meus amigos e colegas brasileiros. Good afternoon for all of my colleagues who do not speak Portuguese as well. My name is Flávia de Almeida Dias. I am an associate professor at University of Amsterdam, and I am also part of the ICHEP, the Dutch Laboratory for High Energy Physics. And today I want to talk to you about diversity and equitable opportunities. And I wanted this to be kind of a conversation, but this is not just a conversation about people, but I also want to convince you this is also a conversation about science and excellent science. So this equity, diversity, and inclusion, it's something that has started at ICHEP for the past 4 years. First time we had a plenary talk on this in 2022, when Johan told us about why EDI matters and why we should be thinking about this. In 2024, we had Tracy telling us about understanding the barriers and opportunities. And very recently, also at LHCP, we had Delia's talk about a similar thing. So I don't want to go over again the same things that you hear all the time, redefining what those things are. I would like to continue looking a little bit more forwards. How do we build collaborations where everyone can contribute and grow and lead? And then see how we can go at the dialogue from there. First of all, particle physics is no longer an individual endeavor. Even if your theories nowadays, our collaboration are getting larger and larger, and of course in the experimental communities, those are very large collaborations. When you think about what do you want from a collaborator, you can think about some of the things which are obvious, right? You want them to be smart and have good technical ideas. You want them to be technically competent. But it's also important that your collaborators have other things, such as creativity and trust and critical thinking. It's important that we all feel recognized within a collaboration, that we respect each other, that we have open discussions, and that we have, very importantly, different perspectives that we can bring into this. So the idea here is that all of our discoveries, they are currently built on collaborations, and the quality of our science, or the quality of the new physics we can discover, really rely on the quality of the collaborations that we build. Now, you may think yourself, what does equitable opportunity then looks like? So if you think about the scientific career, how do you build your scientific career? Every step, every opportunity that you get and that you took, it's what brought you where you are right now. And then I invite you to think a little bit about who else gets to do the things that we did in order to be here in our career. So who is encouraged to ask questions? Who is well mentored? Who is recognized for their work? Who is here giving talks? Who is nominated for leadership roles, trusted responsibility? And who has the confidence to disagree, in particular to disagree with a colleague who is more senior than they are? So this is something that we have to examine. Each of those things, they may seem small, and they may seem very neutral, but it's each of those small opportunities that will bring us to have our career, and that is going to have the things which are important to build the next generation of scientific leaders. So this is a room full of physicists, and what do we like? Well, first of all, we like papers. So throughout my talk, I have a lot of links to different papers, and if you would like to read a paper that is not about physics, please click on them. But we also like data, right? So let's take a look in some of the data, what the data tells us. Currently, we have, for the large LHC collaborations, we have between 20 and 25% women. And in this case, women is defined in the binary way because this is how the gender are recorded in our database. And you can ask yourself, how do we lose this talent then? On the left here is just a pie chart from LHCb gender averages. And on the right, we have this very new plot from Atlas showing the retention probability. So on the y-axis, you have given a year, time since entry in the Atlas collaboration, what is the probability that this person will stay on the Atlas collaboration? And then you have here in orange for women, in green for men, which is very close to the overall average in blue, because we have more men in the collaboration. One thing that you see here is this is very large slope in the beginning. This is kind of expected, because most people will start in the Atlas collaboration either as a student in a short contract, or then they're going to be becoming postdocs, and not everybody stays for their whole career within Atlas. And then this stabilizes a little bit more once the time goes beyond 10, 15 years since entry on Atlas. But one thing that you can see here is that the women curve is systematically below the men's curve. So we do lose more women over time within their career than we lose men. But not everything is bad news. We do have progress. Progress is real. If you've been into a scientific conference 10 years, 15 years, 20 years ago, you know that the demographics is changing, especially across the younger people that we see, the younger faces that we see. You can see here, this plot is from Atlas, but it's very similar in the other collaborations at the LHC, that we have this steady increase over the past 20 years on the fraction of women in the collaboration. And we have this sustained upward trend, which is across all of the collaborations. However, this is a little bit uneven. So the CMS plot shows us something interesting that you see in here. This is the fraction of women starting for non-doctoral students, doctoral students, and then they go lower and lower. And you can see here for engineer and technician, they're much lower fraction than you have for the students. And is anybody here surprised to see that the fraction of administrative staff is over 60% women? I don't see any hands. So the idea here is that even though you have the progress is real, we have more women, just aggregated data like this is not enough. Think of this like measuring a total cross-section and measure the differential parts. We do need to have all of those differential information for us to understand a little bit more where are we making actual progress and where we can do even better. Another thing is that we keep showing these gender plots, and you may say, hey, but gender is not the only aspect of diversity. The thing is, gender is the aspect of diversity that is easy to make statistics about, because when we join a collaboration, we give CERN, for example, our passport, and then there will be a gender marked in there, and we can use this data. However, diversity is much more than gender. And this is very important because all of those different aspects of diversity will shape us, our experience, in a very different way for different people. So, for example, within the same broader category, women, we're putting together people with different ethnicities, people with different nationality or immigration status, with different care responsibilities. Maybe you have children, maybe you take care of your parents, people with different language and culture, sexual and gender diversity. And all of those aspects we cannot really monitor. In many countries, it's even illegal to monitor some of those aspects. But this will really shape our own experience in the field. I will use here a particular case. I'm going to get a little bit personal. In my case, I am Latina. English is not my mother tongue, and neither is Dutch, which is the language where I live and teach. I have had visa issues where I couldn't go to a conference, for example, because I got the invitation a little bit too short, and it wasn't just enough time for me to go and acquire a visa. I have been an immigrant during most of my career, and I continue being an immigrant in the country where I currently live. I am also LGBTQ+, and this also brings all those aspects of myself, brings my very unique experience, and this helped shape some of the opportunities that I had, and also some of the many opportunities that I didn't have, or things that I had to fight a little bit more than some of my other colleagues. Some of you have heard about this metaphor of the leaky pipeline, that as we go forward, you have less and less women and minorities in science. And one of the things is that if you think about a leaky pipeline, it really looks like it's a static thing, right? Like it's a really passive thing. Well, there's this pipeline, people just leave, and that is just how it is. I don't like this because it puts a little bit of the blame on the people who are leaving, while the blame is actually on the structures and the system that makes things much harder for us. So this paper here that I link on the slide, it shows instead this ladder that shows you that different people will have different obstacles which are structurally there in the system. And they are not just personal characteristics. Some people will have language barriers. They will have different access to mentoring. They will have different issues with mobility and visas, bias and discrimination, career responsibilities, funding, and in the case of early career scientists, for example, stable contracts. The lack of stable contracts will really change how you live your career, right? And the idea here is that I don't want the system to just look at people in this ladder and say, well, you just have to be more resilient. We have this survival bias that the fact that I am here means that I was able to climb up into my career achievement, but I don't want other people to go through the barriers I had to go. I want the system to recognize that this is a systemic issue and to remove those barriers so that everybody can have the same access to the same kind of physics results. For that, you need actual institutional action. So I will show an example from CERN. So this is the 25 by 25 that was installed in 2021 to try to increase the nationality and gender diversity between staff and fellows at CERN to 25% by the year 2025. The idea here is very good because you find an objective, you put a time frame into it, you put the institutional responsibility that you have to achieve this, and then you have a very measurable outcome that you can go and see what is your result at the end of this. So you can see it here that this is from the final report of 25 by 25. If you look into this pinkish curve, this is the percentage of women between the fellows and the grads. And this is indeed now at 25%, which is very good. But you can also see, for example, that if you look to all staff, this is this line in here, and this is about 11%, meaning that if you do the average between the staff and the fellow and the grads, we are about at 16%. Those are the percentage already of the people in STEM only. If you look at also at administrative staff and things like this, then this ratio changes a bit. So I think this kind of institutional action is very good because it means that the institution is recognizing that there is something that can be done within the system. But of course, having a target, okay, we passed 25. We shouldn't just be, this is over, right? So now we have a new DG. Hi, Mark. And the continuation of this is then the sustained action. So now we have what we call CERN Inclusion Matters. So the idea here is to be a little bit more broad and have established CERN as a beacon of inclusivity. And we have one of the actions here that we call 50 Inc., which are 50 inclusion actions between 2026 and 2030. And those actions will then have the target to have a foundation, not an endpoint. So we keep improving, we keep listening to the community. And if you have one of those actions, you can submit your proposal using this QR code. So it's very important that CERN is doing those things as an institution. But one institution, it's not enough. In order to have change, we have to have a whole ecosystem because different people will have different needs. So here I have split things into two. On the left, you have what I call structures that create accountability. So those are some of the experiments, this is not an exhaustive list, that have a diversity office, a diversity, equity, and inclusion office of something of the sorts, which are organizational things within the experiment that will, for example, collect actions, do training, collect statistics, and very importantly, communicate with the people in power so that we can effectuate change. So these slides are very clickable. So if you click in each of those logos, you're going to go directly to the diversity office of each of those experiments. But we also have something which is a bit more grassroots. So we have a lot of grassroots network which are there to create community. So some of the oldest ones are LGBTQ plus CERN and Women in Technology, but we also have SNAC, which is supporting neurodiversity at CERN, the Disability Network at CERN, the Gender in High Energy Theory, and for example, the LHC Early Career Scientist Fora. So it's very important that we have both of those parts, the institutional part and the grassroots movements, so that we can have both accountability and we can have community. One of the things that those really help us with is to have representation. When I started undergrad over 20 years ago, we were about 10% women in my group, in my course of the bachelor's. Right now, this is much more. I teach a first-year course, and this first-year course that I teach has 200 students in Amsterdam, and I see way more than 10% women, and I'm very happy about this. And what I'm the most proud of is the fact that they see me there, and they see themselves in there, which is something that I didn't see in my first year of undergrad. And every time that I go and I try to recruit, for example, students to do bachelor projects or master projects with me, all of those young women who were in my class, they come after me. And I think this is really important to show that they really being representative, the representation is really important. So this case is two of the actions that we normally do within our field. So we have February 11, which is the International Girl for Women and Girl in Science. And then we also have LGBTQ STEM Day, which is at the end of November, I think. Another thing is, it's not just about wanting people to come into a field. We want our field to be accessible by design. So this is some of the things that we have highlights from our parallel sessions. We had Professora Rita de Cássia dos Anjos showing us two things that she's involved with in order to improve accessibility to people who are visually impaired. One of them is this elementary particle card game, and the other one is the tactile Pierre Auger Observatory, both the detectors themselves, so when you go to the visitor centers, and also those plates where people with visual empowerment can go and they can see these event displays of Pierre Auger. One of the things, this is mostly geared towards outreach, but what we should think about is when you're writing something, who can access your lectures, your plots, your software, your meetings, your conferences? I think a lot of us felt a little bit how it is when you're listening to the politicians yesterday. So for you who do not understand Portuguese and you had those captions, they were hilarious, right? You could really not understand what they were talking about. Imagine now, this is the Zoom captioning that you have for every single one of your collaboration meetings. It's not as funny now, is it? It just means that you really cannot collaborate with your colleagues in the same way that people who can hear can collaborate with your colleagues. Another thing is about accessibility. Talent is everywhere, access to opportunity is not. So this is to highlight Kate's parallel talk on the ICTP Physics Without Frontiers. And the idea here is that you have this program that goes to places which are isolated based on geography, based on conflict, or based on lack of resources. And then you have those locally shaped projects with hands-on scientific training, mentoring, and research pathways. And the idea here is that we can get these people integrated with us, our scientific community. This program is huge. It's now present in 56 countries and 180 universities, and it has had more than 16,000 students who have attended some of this. The idea here is that global science requires building pathways where the talent already exists, and if we want to do the best physics that we cannot afford to lose talent just because all of those very good people are in countries where they cannot access our science. Finally, I'm talking about all of those different things. So what does Science Without Frontiers and having a Braille card game and CERN 25 by 25, what does all of those things have in common? They seem like they're very different things, right? But the idea here is that they all follow kind of about the same structure. You have to listen to the people to understand all the barriers as they are experienced. You have to design together, and you have to include the people affected to understand if this is what they need. Then you have to find resources, money, implement those things, assign responsibility, time, and funding. And I will be doing a lot of this because a lot of people who do both outreach and EDI work, we don't get money to do this. We are volunteering a lot of our time, and oftentimes it's not even recognized in our own career, for our career progression, that this is important work, and this has to change. And then you have to have something that is measurable and that they can improve. And then here the big thing is that nothing about us without us. You can only have real inclusion when changes are there to see how science is organized, taught, and shared. Everybody here have some power. Some of you in some sphere of influence. Some of you will be perhaps just a master's student to supervise. Some of you are head of institutes, laboratory directors. And everybody can do small things in their daily lives, which I have listed in here, to make things more inclusive. The same way that careers are done by all of those small opportunities that you accumulate over a career, an institution is done by all of those small steps and small decisions that you decide to do a little bit different so that you can build a system that is more inclusive to everybody. So before you decide on anything, you have to ask yourself, who are you designing outside of this plan? So finally, I would just like to finalize here saying that the future of high energy physics, it's a people project. We have today's collaboration. We are gearing towards the high-limit LHC. We are gearing towards future colliders and other experiments. And we want to have the discoveries that we cannot yet predict. But we cannot do any of those new discoveries if you do not keep and you do not attract the talent and the person power that you need within our experiment. And just to say thank you, I have here a photo of Natal being an ally to the LGBTQ community.
Thank you, Flavia, for that very motivating talk. Now we can take questions and comments for Flavia. That one over there. Please say your name when you ask your question. Thank you.
Hi, I'm Laura Montano from CERN. Thank you very much for your talk. I thought it was a very, very good overview. I was wondering if you could comment on the interplay between the roles that institutions and collaborations in high energy physics have on implementing DEI policies, because they're often not aligned. Several institutions can be part of the same collaboration and disagree in the way that they set up their priorities regarding DEI.
Yes, so this is that's where things can get a bit complicated. So for example, right now, if I can give a concrete example, some of the additional material I have on the backup were from US institutes about diversity and inclusion, and they're all offline now, because sometimes a whole country decides that an EDI policy is not something that you should be looking into. I think it's important to try our best to do whatever is the most widened policy of something. But I think for the in terms of where you're employed, it might change a little bit how those DEI policies might affect you. But I think in how we collaborate with our colleagues, there's a lot of things which would still be a common goal, a common code of conduct, common things that we can do regardless of what's your particular EDI policy with your employer, for example.
Another question? Here in the front, please. There's a mic.
Thank you for your presentation. Having thought about this a little bit, it seems to me that when you make your presentation, then the concentration is indeed on the people we try and keep in the field. However, probably the more important role for particle physics, or any physics, is the people who leave physics and go into society and improve society. So I was just wondering, have you guys given any thought to how you handle that transition? Is the transition also negative?
I think the point here is not that the transition outside of physics is a bad thing. And I think this is one of the big things that we sell, right? Like, we do train people who are very skilled at problem solving, and we do train people who are very skilled at collaborating with others. And we do export a lot of people outside of physics into society, and this is very important. What my approach is to say is that if you do have that transition happening more towards one specific group than the others, maybe then it means that the system of the physics is not being the best for a specific group of people.
Yeah, my point was rather, is the work we do in the field negative and limited also for the people who leave? I understand that we're trying to help the people within the field, but we should also think about whether or not the people who leave have also had a good experience.
Yes, I agree that if people who leave, we should be sure that they are not leaving because we're making their life hell within the field. But we also try to solve one problem at a time. I would really hope that we can make physics inclusive enough that people leave for other reasons, like they want to make money or live in the same country as their partners or things like that.
Do we have time for a last question? One quick one, thank you. The other microphone is arriving.
Hello. Okay. Thank you very much for the very inspiring talk. I was wondering if you have, if the diversity, so either the offices of the collaborations, for instance, or the organizations have materials that could share with other institutions, because I was searching sometimes for questionnaires about unconscious biases, these kind of things that could convince my university that there are some factors, a need for these kind of things, and I have not been able to find anything.
I can speak for all of the diversity offices of all the collaborations. The one I'm familiar with is the Atlas one, and we do have in our Twiki a list of resources at the bottom of the Twiki, which are general resources and things that can be shared with other institutes and things like that, for example.
Thank you very much, Flavia. Yes. Now let's welcome Juliet. We will talk about sustainability in high energy physics.
I don't think it's, oh, now it's on. Okay. So you may be sitting there and thinking, I'm a particle physicist. Why should I care about sustainability? And my answer is that sustainability is already changing how high energy physics is designed, funded, operated, and judged by the public, as I will show you in this talk. Considering sustainability in HEP is a cultural change that needs to happen, and I believe is already happening. Okay, but let me take a step back and define sustainability. I like this definition from the UN, which says it is to meet the needs of the present without compromising the ability of future generations to meet their own needs. And we often talk about these three pillars of sustainability. There's the environmental one, which probably you're already thinking of, so things like considering the sustainability of energy, emissions, materials, water, biodiversity. But there's also the social aspect of it, so sustainable education, access, equity, and trust, everything that Flavia just talked about. And then also economic sustainability, so sustainability of resources, long-term value, maintainability. So the focus of this talk will be on environmental sustainability, but you see it's not an isolated issue and directly connected to education, outreach, diversity, and inclusion. So directly connected to Kate and Flavia's excellent talks. Okay, maybe now you're sitting there thinking, okay, Juliet, I want to care. But the problem is enormous. What can we realistically change? And my answer to you here is that we can make an impact at every stage of research. And the reason I think we can do that is because our consumption follows what I might call the research life cycle. So we consume from the level of constructing our tunnels, caverns, accelerators, detectors, and then we consume when we operate those accelerators, detectors, and the buildings that house them and us. Then we consume when we operate our experiments, so mostly on the level of gases, but maybe also electronics. And then at the level of computing, so the simulation, the resources that we use to process and store our events, and then the connections we make, so travel and procurement of goods. And then we also consume maybe when we reuse and retire both our data and our detectors. And the other point I want to make is that the field has been changing, though. The old question was, how big is the effect? So we did footprinting. This means we made measurements, inventories, annual reports. This is all excellent. We're continuing to do this, and we should. But now the new question is going beyond that and saying, what and how do we change as a result? So we're making actual decisions based on this footprinting. So decisions on design requirements, project approval, operating choices. And you don't have to take my word for it. the proof is in the pudding for these for decisions. So, for example, the European Strategy Update recommends detailed life cycle assessments at each stage of new proposed projects, and that the community should continue and intensify efforts to develop and adopt sustainable solutions. And then the CERN Council has adopted this recommendation. Also, the Laboratory Directors Group is developing common indicators and guidelines, and also its Sustainability Working Group has received a second mandate for the 2026 to 2028 period. Also, there's CERN 2030, which has operational and environmental objectives. So the plot on the right here shows you the CERN greenhouse gas emissions per year, and the target is the green horizontal line. Also on the experiments, so ATLAS and CMS have resistive plate chamber and cathode strip gas reduction programs. And on the computing side, so we have the worldwide LHC computing grid, the WLCG. This has a strategy for sustainability as well. So measurements are great, but they need to affect real change. And to make decisions, you need a credible plan. So this could be a plan for a lab, a collaboration, facility, detector, computing system. But a basic idea here is that we have to measure our baseline, measure our boundaries, then set targets. This means dates, owners, resources. And then we have to actually change the design and the operation. Maybe we choose different options. And then, continuously, we should report the progress, report the outcomes, not only our intentions. So there's an example of this nicely from NICEP. Basically, they measured their 2025 baseline, and then set a target for 2030 of reducing their CO2 by 55%, and then a further target for 2035 of 90% CO2 reduction and 10% CO2 compensation. So what makes a plan credible? If you have a target, owner, resources, and transparent progress. Okay, and here are some major initiatives that I've classified based on facilities and accelerators, detectors, and computing. For example, the LDG sustainability panel that I already mentioned, also ICHEP, ICES, and also there's accelerator guidelines. Then on the side of the detectors, there's the DRD1 collaboration and the EcoGas at GIF++. Also, there's experimental programs like the ATLAS and CMS gas reductions that I already told you about. There's also the ATLAS has a sustainability forum. And on the side of computing, there's the WLCG Sustainability Forum that I mentioned. For example, the HEP Software Foundation, Punch4 NFDI, sorry. And many of these are sort of top-down initiatives, but there's also bottom-up initiatives from communities. For example, Sustainable HECAP, Sustainable HEP Conference, Labos 1.5, ARAM Action Group, and then communities at the level of institutions. For example, making roadmaps like NICEP has done, also maybe local forums and training. And the talks from the parallel sessions I linked to here, these are all directly applicable to these initiatives. So you see that the field doesn't necessarily lack ideas. The hard part is ownership, resources, and follow-through. And out of these major initiatives, I wanted to highlight the Sustainable HEP Conference, which happened just a couple weeks ago. And it was totally online. And I mention it because a lot of the material that I'm going to show you today was taken from that conference. So as I showed you 2 slides ago, maybe already hinting, the main levers that we have to be able to work on our consumption is at the level of facilities and accelerators, detectors, and computing. So this also will be the outline for the rest of my talk. So on the side of future facilities, the name of the game here is to assess the full life cycle early. So if this is a sketch maybe of a life cycle, basically we go from concept, design, and procurement, and then to the construction stage, then operating our facility and even upgrading it, and then the last stage is decommissioning it and reusing it. And one thing that we should do when comparing different alternatives is to use the same boundary conditions. But also the other thing that you see when looking at this is that the earlier the assessment, the larger the available design space. Because as we go through the life cycle, the freedom to change the design decreases. So what we need to do is also update the assessment once our designs mature, and then that assessment must be allowed to change the design. And then, okay, on the side of accelerators themselves, here sustainability is an engineering problem. So on the side of radio frequency cavities, here what we often want to do is convert power more efficiently. So this can mean using better sources, active tuning, and lower cavity losses. On the side of cryogenics, here the goals are to keep the heat out and cool more efficiently. So this can mean operating at a higher temperature for our cryogenics and also refrigerating more efficiently. And through all of this, we should think about recovery and lifetime. So recovering things like the beam energy, waste heat, and keeping the resources in use and having a modular and repairable systems. So the idea is that energy, material, and lifetime must be design requirements and not late optimizations. Okay, moving on to the detectors themselves. Here I'm going to focus on detector gases. So gaseous detectors are widely used across HEP. You know this. For example, resistive plate chambers, like this diagram at the bottom. These use a mixture of C2H2F4. So the specific instance of this that we use is R134A with SF6 and isobutane. And other systems, such as the CMS cathode strip chambers, use CF4. But basically, these fluorinated gases that I've highlighted in red here have a much higher climate impact than CO2. So what can we do to lower emissions? So I think there's maybe 4 general classes, routes that we can take. So we can repair, reuse, replace, and redesign. And I'm going to explain these 4 in context with examples on the next slide. But just to first say that no one of these solutions should work alone. And also you might think, well, okay, why can't we just replace the gases? Shouldn't that be the most straightforward, easiest thing to do? But it's not always easy, actually, because replacing the gas can change the detector operation and performance. So using eco-gases is really a detector R&D problem. Okay, so let me give you some examples of recent progress, and I'm taking RPCs as my case study here. So on the route of repair, so I have an example from CMS. So during long shutdown 2, what we were doing is to patch the leaks in the RPCs one by one. But then since 2023, we have a more robust procedure in place where we are replacing all of the pipes per chamber. Sorry, I meant to highlight the pipes here. And actually, we've seen stable performance with this. Also, I have another example from CMS, but here on the idea of reusing gases. So basically, you have gas coming out of the mixer and then going to the detector, and then there's an exhaust. And actually, 90% of the mixture now coming out of the detector is recirculated. And also, out of the exhaust, we can then separate the gases, and then the main fluorinated gas is recovered, now with 80% efficiency. And this we've been doing since July 2023. So those recirculating and recovering the gas is to reuse examples in CMS. Then I have another example of replacing gases, this time from Atlas. So from January 2025, they've replaced 30% of the main ionizing gas, this is C2H2F4, with CO2. And then also, they've halved the fraction of SF6. And I should have mentioned, SF6 is a tiny share of the full RPC gas mixture, but it has a really high global warming potential. And the results of doing this is that the mixture overall now has a 27% lower global warming potential, but in addition, up to 30% better intrinsic RPC time resolution. So better for the environment and better physics. And my last example is of redesign. So this is from the EcoGas at GIF++. So here, redesign needs qualification. After irradiation, folks at GIF++ have shown basically that you have a shift in the operating voltage. So you can see from the plot, these two curves at the top, the turn-on curves have shifted with respect to the high voltage thresholds. And this shift is seen for both the standard and EcoGas mixtures, but you see that then the stable performance is retained. And here, when we're redesigning, we need to qualify for the required rate and lifetime. So the idea is that we need to repair, reuse, and partially replace now, redesign where needed, and qualify for the actual rate and lifetime. Okay, and then moving on to the third part of my talk about computing. So first, we need to avoid waste. So when you're designing software and maybe setting up to submit jobs, first think, what is this software for? How long will I need it? Basically, you should think about the entire life cycle and then design accordingly. Then when you go to submit jobs, before you submit 10,000, 100,000 jobs, think, do I need to submit these jobs? Consider your CPU, memory, storage. And then before you actually submit, test. You can do unit tests, integration tests, system tests, or continuous integration, and/or continuous integration to help you understand the impact of what you're doing. You can also think about reusing samples. And then documenting is inherently part of the process. And I firmly believe that sustainable computing must become inherent part of every particle physicist training. And I have an example here from the OpenLHC Monte Carlo event generation. And here the idea is to generate once and reuse many times. So what they've done is you can see that this is working from this plot at the bottom here, which shows you the invariant mass of a dielectron system with CMS data in black and the Atlas open event generation in red. And you see really nice agreement. So basically, this can have us save money because we're not generating more events, we're not having all the resources to do that, and also decreased environmental impact without an impact on the physics. So you see that this improves the reproducibility and access and touches on not just environmental sustainability, but the other aspects, the other pillars of sustainability as well. The other thing to think about in terms of computing is measuring the energy efficiency. So this is an example from the high-low project here, and they're defining they've measured this energy efficiency. And this is really the number of useful events per joule. And they've measured this by measuring the throughput divided by the power consumption. So that's what's shown here on this plot for a number of different GPUs, and the energy efficiency is on the x-axis. And the one in red is this RTX Pro 6000. So this one was actually the fastest GPU, but you see from the plot it's not the most energy efficient. So that's maybe surprising. And also the last row is RTX Pro 4000. This is the most energy efficient GPU, but it is power limited. So our expectations our assumptions may be off here. So the point is that we should measure the real workload, not only the rated power, clock speed, or peak throughput. Also, I wanted to highlight an example from the WLCG. So here they have a HEP benchmark suite where they're measuring the machine load, memory usage, memory swap, and now actually the power consumption. So that's really great, and here they have benchmark jobs that have been run on real grid nodes under production workloads. So basically, the idea is that better hardware choices require comparable measurements of power, performance, and site overheads. And finally, a bonus slide maybe on computing. It's 2026. I'd be remiss if I didn't mention AI. So what can AI do? Can that be sustainable? Well, it could expand the workload. AI can be added demand. If you have an existing workflow and you put in a larger model and more inference, this has risks. If you don't define the physics requirement, if you have maybe repeated retraining instead of reuse, if you have increased model complexity without an appreciable analysis level gain, if you use, for example, a general purpose LLM where a small tool would do. On the other hand, AI could reduce your workload. So here, maybe an example is using AI as substitution. So instead of having expensive simulation, you can have a validated fast surrogate. So one example is from generative detector simulation that I took here from this talk at the ICHEP conference. And basically what they showed is that CaloClouds 3 runs up to 100 times faster than GANT4 on CPU with the benchmark they've chosen, and up to 1,000 times faster on GPU, while still maintaining good agreement with GANT4, for example, in photon multiplicity, as that plot shows. So basically, AI, the risk is that as efficiency increases, we just consume more. But we can overcome that if we define the physics requirement, measure the full cost, and then stop when that requirement is met. So as you've seen throughout these examples of accelerators and facilities, detector gases, and computing, that a common theme is reuse. So reusing, for example, helium in cryogens, reusing waste heat locally as is being done from LCB to locally in buildings in Fernie Voltaire, recovering gases and recirculating gases, and software using reusable tests and workflows. So reuse is also widens access. There's, because I wanted to mention this because shared hardware, shared samples, tools, and shared training lowers the barriers for smaller or poorly represented groups. So what can you do? You can ask for information and share it. You can communicate sustainability in all aspects of your work, because I've shown you that it impacts all aspects of your work. You can teach it, like we're doing at DAISY. You can request reporting and join or create sustainability efforts. You can measurements. Many of you are experimentalists. I know you love to measure, and the theorists, you're just jealous. I know you want to as well. You can measure your energy, gas losses, etc. You can also avoid waste. You can reuse data, reuse your software, reuse your detectors. And you can make sustainability a design requirement. Make it a design requirement at the level of facilities and future colliders, detectors, and software. So finally, I've sometimes heard sustainability would be great, but it's limiting me. I wanted to do the best, I want to grow, I want to push things forward. But sustainability is not what stops us from doing ambitious science. It is part of how we make ambitious science possible. Measure honestly, choose early, build for the full lifetime, and share what can be reused. Thank you.
Thank you very much, Juliet. Now we have time for one or two questions. Please raise your hands. There is one back there, please.
Hi, thank you for the very nice talk. I was wondering if you could speak a bit to sustainability in supply chains for things like rare earth minerals, which are used both in our computing infrastructure and in building our detectors. I often don't hear this talked about, that these rare earth minerals are harvested in very unsustainable ways. And I often find myself wondering what ways can we as physicists, what can we as physicists do about that frankly unequal and destructive supply chain? Are there things that have been done? Are there things that we can do?
I think this is a very interesting point. And I'm going to admit ignorance here. I don't know very much about it, but I think it's important, and it connects directly to issues of access and you know, frankly, global issues. Thanks for for bringing this up. I think we need to work on this. Thank you.
There's another question here in the front.
Thanks for a very nice talk. So, as you mentioned, some organizations and institutes have pledges to reduce CO2, and we know that this often includes strong pressures on researchers to not travel to conferences, which would be, so these people would not have come to this conference, for example, if they're from Europe or the US. And this can be quite unfortunate, as in-person exchanges are an important part of science. So do you have any suggestions on how we can compromise between the two?
Right. I think we have to agree and talk to the people, our institutes and larger organizations, to convince them that it's not a one-size-fits-all. We can't just, unilaterally reduce our travel evenly. We have to, one thing we can do is each individually think, okay, do I need to travel for this specific case? Would it make a difference, or can I connect on Zoom for it? So I think it's an ongoing conversation that we need to have with ourselves and with our institutes, for example, to explain that exactly, you're right. Access and there's no substitute in many cases for being in person, and I think anyone can understand this. So we have to work with our policies to not have a one-size-fits-all policy.
Thank you.
We can allow one more question. Are there any questions or comments there? Professor Jorge.
Thank you for your nice talk. I wonder if you can comment on this program related to the boundary conditions. How this depends on a political condition, economic condition, because this sometimes offers some limitation to kind of planification.
A limitation of what? Sorry, I missed the end.
In the sense that you want to have some program that will improve certain characteristics, efficiency and so on, but determining in a certain historical situation, it will happen that certain boundary conditions from the economic point of view or a political situation will affect that. So how do you manage this?
Yeah, no, it's an interesting point. Yeah, I'm not sure. I mean, I think basically, well, one thing I think is that we need to have a transparent dialogue about it. We have to communicate with the people, with everyone, to make it clear, where things would start to affect us, and the impact that it can have if rigid boundary conditions, for example, are set. So yeah, I think a lot of conversation, really, frankly, is needed.
So thanks. With that, we can close this vlog and we go to the coffee break. Thank you, Juliette.